Hi, and welcome to this week's Social Science Data Lab. I'm very happy to welcome today Christopher Klamm, who will present on transformer-based language models. The Social Science Data Lab is an event series at the Mannheim Center for European Social Research that provides a platform for early career researchers to present tools and methods for the collection, management, analysis, and visualization of data in the social sciences. Our speaker today is Christopher Klamm. He's an interdisciplinary researcher at the Data and Web Science Group at the University of Mannheim. His research focuses on the intersection of natural language processing and computational political science. And in today's talk, Christopher will talk about transformer-based models, which have recently gained quite some attention, especially with the release of ChatGPT. And in his talk, he will examine the components that make up these models and show how to train them for your research. He will also discuss some limitations and challenges, such as open source availability, the growing need for resources, responsibilities, and others. Some disclaimer, we're recording this live stream in active speaker mode. So audio from on-site and remote attendees will be recorded. And if your video is on while asking a question online, your video will be recorded as well. And for those of you joining online today, you may ask questions by raising your hand or posting your questions in the Zoom chat, and we will read them out for you. Christopher.
Hi, everyone. Thanks a lot for having me today. I'm really happy to be a part of this series. And transformer models gained a lot of attention. Also, the new ChatGPT thing is in every kind of news media and also on the social media. So for me, preparing this talk, it was a little bit tricky because 2 months ago, it was quite easy. We had these transformers, language models in the NLP, in the natural language processing domain, and just a bunch already know what is a language model, what is a transformer-based language model. But now the ChatGPT thing is all around. So we have a lot of new cool tools, new architectures, and a lot of new stuff coming out day by day. So it's just looking at the last week, we can find a lot of new cool projects. So in this talk, I will try to cover a lot of new things, also from the generative language models, ChatGPT. But for me, it's also important not just to have the newest models in this talk, but also to talk about the background, the basics. Especially in this talk, I'm trying to answer different questions. First question is a very basic one, but we want to know what language models are. And the question is why we need a new language model, a new kind of language models, if we already have one. So the question is why we need the transformer architecture. And then I will try to give you an overview what is so important and so powerful of this new architecture. And especially having these different kind of language models, the ChatGPT thing, but also BERT, the language model, which is maybe a really prominent one. And they share some similarities, but they are also quite different in a lot of aspects. And also what is important for you as a researcher or for you as someone who wants to apply your own model or also to use existing models, we will look into the training and the use of transformer-based models by using HuggingFace, a really cool library project, startup, and also open science initiative. So there's a lot of things to learn about how to do it yourself. And then at the end, we will look into the more problematic aspects of having these large language models or language models in general, and also think about what are to-dos on our agenda to improve the use, but also the development of such models. Let us start with the first question about a definition of language models. So first of all, just to say, okay, we have a new architecture and these kind of models are trained on a large amount of data. Here in this talk, we will be more focusing on textual data, but you can also think of images and videos and all the other things, and audio, for example. And the cool thing is here also for this kind of models that they can understand the thing more in context, the words more in context. So we have a lot of applications, not just the dialogue thing or the question answering thing, but also classification, or translation, or a lot of other things. So, and the important aspect here is from an empirical side, they show an amazing performance in applying the new architecture to such tasks. So, but coming back to the question of what is a language model, and to have a very basic starting point, you can think of a language model as something that represents the language used by an entity. It's a very basic definition. And here an entity can be, to be honest, everything, but here you can imagine of a person or a domain or a text type. You can think of Twitter as an entity. You can think of books as a really big entity of different kind of books, for example, in English, which is also a specific kind of an entity, English books. So, and the language model is now someone who read a lot of books. You can think of Lisa, for example. Lisa is just a girl reading a lot of books during her summer break. And she gets an understanding of the kind of language used in these books, in the English books. This means she learns the different words, the different context of these words. And if you ask Lisa to say something about these words or to complete a sentence from this domain or from these books, then Lisa get an understanding of what could be possible next as a word or a sentence or a context. And here we have these new automatic or language models from a supervised perspective or an unsupervised perspective in this sense. We are now able to let the models do the learning, the reading, thousands of books, of different kind of books. So now there's a model with an understanding of English books, for example, on politics. How such a language is represented is now included in such a model. It's about an understanding of the different patterns and relationships between words and phrases from such a domain. And here you can think now of a possible use case, which is also a very simple one, to fill up the gaps. So it's a test for Lisa and for a new model trained on a lot of books. And Lisa is now thinking, what could be a good word which is suitable for such a gap? So, and then Lisa might come up with graduation here. And the model is doing a little bit different. Here, the idea is that such a language model estimates the probability of different words over a vocabulary. Let's say 20,000 possible words for this gap. And now our model is checking the most likely word and presenting us the probabilities over the big vocabulary. having such a language model is just a way of representing a language in terms of a possible distribution of more likely to have a next word, for example, in a sentence. But you can think of a lot of different kinds of ways to learn such distributions. And in the early days, the natural language processing started by using rules. To have a specific rule made by experts to say, okay, after a word such as politics may follow a specific other word in terms of their word category or in terms of specific relationships, but you have to handcraft all of these rules yourself, which is a little bit tricky and complicated, and you have to do a lot of things to come up with a complete rule set. So that's why the research moved a bit to a data-based approach. And the data-based approach here is a statistical one. It's about counting possible occurrence of words in a corpus or a domain or what we have called an entity. So here you can start without any information, without a context, without history, and just having the probability of one word, one token. So it's the most likely token given the entity, the corpus, the domain, the books you have used or you have in your background to learn what is a good following word. And then you can add more context. You can say, okay, let's say someone is born in, then it would be nice to have born as a history that you may come up with in as the next possible word. But you can also increase the context to have a better understanding what is the next possible word. So was born in. So it's more concrete. But here we're faced with a lot of problems doing it this way. The problem is if you have a long history, you need the exact same sentence in your background corpus, in your domain, in your entity. So that's sometimes a little bit tricky to have exactly the same long sentence, long history again in your corpus, and now during your test, doing your unseen tests now, that's the trickiest part. So we have some problems here, which is often called data sparsity. So some of the histories, some of the anagrams do just occur in the training time, in the background data set, learned, and you have a completely new thing in your test time. What does this mean? For example, we have this training and we have the test, and having an overlap, that's easy. So if it's in the overlap, that's easy to check. But if you are checking an unseen sentence, for example, a dog is chasing a llama, and there was no such a sentence in your background, then it's quite hard for the model to come up with the probability of having this sentence again. So the model is just counting how often such a long phrase or just a chain of tokens occur in the training. And if there's nothing, then the model says, okay, I've never heard of such a sentence before. So I don't know how likely it is to have the sentence. And that's also a problem of the long-range dependencies. So having a short history makes it quite easy to have the same again in the training and during your test. So born in might be a common phrase, a common n-gram. So you might find it in the training and also in the test. So that's easy. But having a long phrase, that's a little bit more difficult. So that's why the older models limited their history to check the possible next word to represent the language. So they're really limited in terms of getting the whole context. They're just a small view of possible words giving a shrinked and dense context. So that's why, as many of you know, there is the new idea, not just to check for the exact overlap, to look for the exact same phrase again, but just for something which is similar in terms of the meaning. And so the idea was not to represent the tokens as a token. The idea was to represent this as a vector representing the meaning. So you have some numbers representing a token, for example, dog, and you learn that in the same context, another animal, for example, a cat, is also often probable or likely to have. So then you have two words which are really similar in terms of meaning because they are often in the same context. So then it is possible that you have never heard about the cat, but you know that it's really likely to have a cat when it's also likely to have a dog. So both share the meaning. So you don't have to look for the exact overlap, you can look for the meaning. So that is what we call word embeddings. So the word embeddings was a big improvement, and I think it's especially in the research domain an often used concept. So the word embeddings are also learned by checking different sentences. For example, if you want to train a language model, you also start with a history, and then you try to predict the next possible word. And here the idea is that you learn the representation in the model, in the parameters here, in the hidden layer of one word to represent the dog, for example. And that was a really important step to not just to look at the tokens, more look at another representation of the words in terms of meaning. So then you have the chance to group and to understand the similarities between words. So here, then you solve, in a way, the data sparsity of the problem that it's just in the training, but something completely new in the test might be a little bit tricky. So now we can look for similarities, and we do not need the exact same words again. And here the problem was that it's a bit tricky also to learn long dependencies. If you have a really long sentence and you want to integrate the context, for example, Obama was born in Hawaii and so on, then you have a long context and you want to integrate this context in the meaning of a word. But having 20 tokens or so, it's a little bit tricky to compress all of these information and to have it in one vector, in one representation of the word. So here the idea was to come up with a model called long short-term memory. So the idea is to have a memory reading a sentence like a human and processing it like a human from left to right. There's also from left to right and right to left, but let's start with left to right. And you get some information about the different tokens over time. You're reading it over time from left to right. And then you're integrating such information to the words, for example, to the in at the end, to predict the next one. So you integrate the whole context by having a memory to memorize the different contexts before a specific word. So the problem here is that there is a concept about the forgetting of information. So you start with a specific token, let's say here in this case, Obama, and then you add to your memory the next root, the next root, and the next root, and you try to create a representation of all of these roots. And here the problem is that the model is starting to forget the first roots over time a bit. So there's much less information at the end about the first root, but the model is not able to focus on, let's say, Obama. The model can just do the time-based processing of such a sentence. And at the end, during processing the in, it might be struggling to think, okay, what was the first root in this sentence? So, and then the context is not that clear. So we are trying to find a method which is also able to take the whole context in mind and to focus on specific words, also at the end, processing the in or the next token. And what is also a problem of the neural embedding thing is that you want, or if you're training such embedding for exact one word and you have just one embedding for a word, then you have the problem that a word can have multiple meanings. But just having one representation per word means you have all of these meanings in one representation, which might be a little bit tricky to distinguish between the different meanings, for example, of the word bank. So could be surrounded by water, could be also in your garden, could be also about money. So it's a bit tricky to have all of these meanings in one representation. So the idea of the transformer-based model is also to come up with some ideas to solve the problem of the context and to solve the problem of the long dependencies. And so here we're now trying to answer the question, what components make the transformer architecture so powerful, and also providing a way to solve these two problems. One core aspect would be that there's a specific mechanism called attention, which is really important to solve these problems. Let's start with an overview of the architecture, with a very simplification of the whole architecture. The transformer model is about having an input, especially the bird model here is about having an input, and the input is also added with some information, some metadata information about the starting of the sentence and also a separation marker. And here the separation, the idea is that you can also put two different sentences as an input to the model. For example, if you want to have these question answering settings, you have a question and you have an answer. So to feed both into the model, the architecture provides a way to show the model that you have two different things as an input, question and the answer. So that's why you need the separation token and the starting token, just to say, okay, here, that's the starting point, and especially the starting token is also important to embed the meaning of the whole input at the end. So it's a more from an empirical perspective inside that the authors of the bird model and also the architecture found out that the first token, the CLS token, is a danced version of the sentence, or it's more an empirical proven way of saying that is the best representation of the whole sentence. We can look a bit further into detail. Here we have the transformer architecture that is formed or constructed with different layers. And the layers are based on two main components. First, it's the attention, and then what is called a feed-forward neural network, which is the same for, it's just another word for multi-layer perceptron, which is the smallest way of having neural networks. The important part here is the intention. But before you feed this information to your model, what is also important here is that we have first the token embedding. So from the word embeddings, we already know that there are some token embeddings representing our different tokens in a sentence or a phrase. But here, it's also something completely new called the position embeddings or vector. The idea here is that we add also some syntactical information to the model. So about the position of a token in a sentence, especially in some languages, it's creating a specific meaning depending on the position of a word in a sentence. And then we have also something what is called segment vectors, just representing the two parts of a possible input. For example, you have these question answering example, then your first segment is the question and the second is the answer. And you want to help the model to identify what segment or what is in the first segment and what is in the second segment. So you just have some information about the separation of the two segments here. And the learning of such a model, so these language models are trained on thousands of books, which is, I would say, the core contribution, that it's possible to encode all of this information, as we have learned from what does a language model do, learning from a lot of different books and inputs, and could be also websites and Twitter posts and anything else. And here it's there are different ways learning this information. And here we have two different pre-training strategies. The first strategy is a mask token prediction. That's why these models are often called masked language models. So the idea is here that you mask out one word. It's like the gap in the test for the language models we had in the first slides. So you mask out one token, and the task is for the model to predict the missing token. And you learn also over the probability of the vocabulary of a model to predict the right word for a given context. So that's the idea, to learn the language, to represent the language. And another way is, for example, to do a next sentence prediction. It's also about the context. You have first, which is also important for having such a separation marker. You have a first sentence, and the model now needs to predict the second sentence, the following sentence, to get an understanding about the context of two following sentences. If you look into different models using the transformer architecture, you will find out that especially the training strategy can be different. So these two strategies are just an example of doing the language representation learning of such models. And now we can think of the core feature of the attention mechanism. Why is it so important and so new, and why is it, I would say, the thing what makes such models so powerful? The problem was that if we want to predict Hawaii in this example, given a context, it's a bit tricky for a model to get an understanding what is the important word of the context to predict the next one. So here, the authors introduce a called weighting function, which is the attention. And now it's possible for the model to focus on a specific subset of the input and avoid a compression of the input. The compression here is, for example, for the long short-term memory models, compress the whole context into one word and then a little bit forgetting the first word. Now here it's possible to say, okay, for this task, especially Honolulu example is important to predict Hawaii, and maybe also Obama or was. It depends on the context and in the model. So here we have a completely different way to focus on specific aspects of the context to predict for a following word, the next word. So the model is able to say, okay, that's important for me to say that Honolulu is the right next word. And the concept here is called also self-attention. You may ask, okay, attention, what about the calculation? The calculation here is that looking at one specific word, the model is just checking the different similarities between a word and the context words. But you can find a lot of different ways to calculate, to define such a weighting function, which is also a research topic, just to define the right function to help the model to focus on the right words. So having this architecture, especially having the attention mechanism here, is a way to solve the long-term dependencies. So I've also already mentioned that there are a lot of different models using the transformer-based architecture. And now we want to look and to get an understanding about the differences between these models. So you can think of first that, as I've shown, the training strategy techniques are different. So especially looking for the generative models, the GPT ones, the important aspect here is that they are trained with instructions. We will see the different contexts and paradigms in another slide, but here the first thing is that you can train a model on different ways. For example, the masked language modeling, predicting the masked token or predicting the next sentence. But you can also help the model with providing a question and an answer, and so different ways of training it for your task or just for the representation of a language. So, and then what plays a very important role at the moment, and especially for large language models, is the training data. I would say often the rule is, if it's possible, you should use as much as you can, but it really depends on your target, task, and domain. What do you want to do? Do you want to classify tweets? Then it might be helpful to train more on Twitter data to learn the representation, the distribution of possible words in Twitter, to get a better representation of the language used in such a domain. If you want to do, or if you want to predict the sentiment or polarization or stance for politicians, then it might be helpful to use parliamentary debates or other texts which are related to this domain. And then you can think of another difference, which is about the model task itself. So it's about the right training data or a specific training data for your domain task, and then to check what kind of task you want to solve. And here you need different training strategies, a different language model which was trained on a different way to solve your task at the end. And what is also important is the number of parameters. So now we have this term large language models. And the large part is just because the number of parameters increased dramatically. So having the first bird model, something about some millions of parameters, now we have some billions of parameters represented. So it's also an open question if we really need so many parameters, but the intuition here is that if you have more parameters to train your model, to learn how to represent a language and to represent specific tasks, the model is more powerful. So that's the current intuition. But it's an open question because we have a lot of research in the direction of low resource language models, dense language models, distilled language models, also doing the same tasks with the same performance sometimes, but having much less parameters to train. So the biggest ones are not just the best ones. It really depends. So to show you, just to give you a picture and an overview of the different kinds, you have the pre-trained models trained on a lot of thousands, millions, trillions of books and other things, which are often called BERT or Roberta or distal BERT, a more dense version. And then you start to adapt these models to your specific task. For example, you want to learn more about the classification of arguments, or you want to classify different policy topics, for example, then you have to train such a model on your specific data. Or you just want to represent the domain more in detail. For example, you have your legal domain, you have some legal documents, and you want to classify the topics in such documents. You may need to start with an adaptation phase to such a domain to learn how the language is used in a legal domain. And then you can do the classification. So these two ways of using transformer models for BERT, for example, are quite common. So, for example, you have a transformer model, BERT, for example, and you want to just create a representation of a sentence. For example, you want to check the similarities of different speeches between the different actors or across the different actors in a party or between different parties. You can create a representation of the speeches in sentence and just check the similarity between these different speeches and the different politicians. That's one prominent example to use it, just to create a representation. Another one is to train a model on your own data set, maybe also with domain adaptation, but first just providing some labels. For example, you have these classic sentiment task, or positive or negative, or you want to classify stance, then you have to show the model some examples and update the model with regard to your task, which is called fine-tuning here. But the new models provide some different paradigms, especially the generative language models like ChatGPT. Here, I would say two paradigms are really important. First of all, which was also proposed in the first paper on ChatGPT 3 years ago, it was the in-context learning, or an example-based specification or learning. This means that models like GPT can you can provide such a model a context of your task and some examples. You show the model how to do a sentiment classification by giving some examples. You say, okay, I like this movie as a positive example. I don't like this movie as a negative example. And I have mixed feelings about the movie, but overall it's a good one. It's also a positive example. And that's your context for the model. And then you ask the model to predict based on a new unclassified sample a class, a positive or negative class. For example, the weather today is really good. So then you expect the model just by giving the context without updating anything, without fine-tuning, without updating anything, just by the context to say, okay, given the other examples, it should be a positive one. So that's the idea, that you don't really have to train some more. You just have to provide a good context, what it means to solve a task. And another paradigm now is the prompting paradigm. You provide the model some instructions to do your task or to ask for something. Let's say for question answering. And here it's more about asking the right questions in the right way to trigger the knowledge of the model to solve or to answer your question. So especially the last one, the prompting part, is getting more and more important at the moment. So we have also think about how to use this for research to solve the question. And the open question is, do we really need the other two things to fine-tune such models on our data? Or is it just enough to describe our task in detail, and the model is good enough to do the task without added training data? So that's called zero-shot classification. If you don't have to train the model again on your data, then it's zero-shot. And if you provide some examples, like the context example, it's called few-shot. You provide a few of samples, and then the model is able to do the classification. So we have these different paradigms, and we want to use these models for our research. There is a library or startup or a framework called HuggingFace, and it's an API, a startup, but also an open source community. And they did a really cool open science project 1 year ago, creating their open GPT model, which is called Blue here. So there is also an open source alternative, which is an important aspect if you want to start using such models. And the easiest way to use HuggingFace to do such, for example, classifications, is to use the pipelines. Pipelines is just a way to have just a few lines of code to specify your task and your data, and to get the predictions out of the box by using existing models from the HuggingFace Model Hub. An example here is that you just have to load a pipeline, and then you have to specify your task. This example is a text classification task, but you can also check out the documentation about a lot of other tasks, for example, also question answer. And then you have to specify the model. And here you can check out the HuggingFace Model Hub. You can find more than 100,000 models trained on different tasks, on different data set. And so you can try out a lot of different model types and apply these models to your text. And here the example is you just have to use the defined pipeline, about 4 lines of code, And then you can use it to check or to provide some data for your analysis on a phenomenon, for example, also for frames, for stands, for sentiment, whatever you want. Here is an example of the different models from the hub. Here you can also on the left side filter for your task, for your language, and also there is a new thing about the carbon footprint of the models, if the models also provide some information on this. And what is a cool thing on this platform is that you have model cards for each card, and model card is a specific concept of describing the models, the model training, the model data, but also possible biases and unintended use. What is maybe also problematic for such models, and especially if you have hate speech aspects and so, or you want to build a chatbot for children, or you want to build something else, you have to check for problematic aspects of such models. In the GitHub repository from this talk, you can find a repository on GitHub. You can find also some hands-on session notebooks, and one of these notebooks explains the use of the pipeline feature. So you can try yourself different existing pipelines by using these state-of-the-art models, for example, for sentiment, but also for emotions and for toxic. And there's also an example at the end about a possible bias in such sentiment models. The bias is about a specific country and the use of just having the country as a trigger for the model to predict a more positive or negative stance, or in this context, sentiment. If you ask for movies from this country, it really depends on the country name. So it's an interesting example to get an understanding of possible biases. So using such models out of the box is often a little bit problematic, and you definitely have to check for your use case what is a possible bias, and why you should test or do a qualitative analysis of some predictions of such models. So having this as a very first and easy step to use existing transformer-based models on your own research tasks, or just to test out the performance of such models. We have also we have a lot of possibilities to train such models on our own. So it's here called task-specific fine-tuning for classification. And the idea is, as I mentioned, is you have a pre-trained language model, for example, BERT. We can also use a GPT thing. And now you want to train or fine-tune the model on your specific task. And that means that you are trying to update the internal parameters regarding your task. And the idea is that having this new data, updating your model, the model is now able to infer new data from the same classification tasks, for example, supervised topic classification. And here's also an example in the GitHub repository, but you can also find a new tutorial on the ANSYS site. It's about also how to train your own language model, and it's really cool because it's also include a section about the explainability of such models or the interpretation of such models. Because the problem is sometimes that the performance is quite well, but such models, for example, sometimes do a shortcut, just focusing on exclamation marks, for example, to classify your samples. But from your perspective, the model should be more focused on specific words. For example, the sentiment, task, you might think of having a positive or negative word in a sentence. And then the idea is that the prediction, the classification of the model depends on such words instead of just focusing on exclamation marks or something like this. So you have a way to check how the model is working from an internal perspective. So that's really cool, and an open research question how to do this, and if such libraries and methods really represent the attention of models. And it's a really cool subtopic, but it's I think it's an open research question. What is the best way to do this? So here's a very small example. You can also find a longer one in the GitHub repository explaining how to do the classification your own. But just to give you an example, using HuggingFace means here that they provide a lot of wrappers for you, that you just have to specify small things for the training. First of all, you have to specify again the starting point, the model which was pre-trained. For example, the bird model could be anything, could be also a smaller one, a distal bird model, or could be the Bloom one, the open source model from HuggingFace. And then you have the model as a starting point, and now you have to define the characteristics of the training for such a model, for the fine-tuning for your classification task. And here the idea is that you specify some training arguments. For example, the number of epochs. It's just the number, how long or how often the model should analyze during training your given data to update the internal weights. And also about how often you want to evaluate the performance of the model during training. Because the idea is that you have to check the performance, the training results of your model after an epoch or after specific steps, or at the end of the training, to check if the model really learns what you have in mind. For example, you want to do the sentiment classification, then you have to provide the model some test data at the end to check if the model is really able to do the sentiment classification on your new task. Because especially cross domains, cross text types, and so it's sometimes not that easy to transfer a model. If your sentiment model is trained on Twitter, then you definitely have to check if such a model really works on Reddit data or any other kind of social media posts, for example. Or you want to apply this model to your parliamentary debates data set, then you also have to check with the test set if the model is really performing that well on such a new text type. And now you have to define a trainer, which is just a way to say, okay, now that's the model I want to use, that the training arguments, how long the training and the logging steps and the evaluation and so on. And then you have to specify your training data and also the evaluation data here to check the performance. You can find a really good explanation in the tutorial on the ANSYS website about how to load your own data set, or you can also check out the repository for getting an understanding how to load your data and train the model. You can just run all the cells in the notebook. Here, you might need to copy this notebook and I think you need a Google account to do this, but you can also just download the notebook and run it locally. So at the end, you have to just say, okay, yes, and now you can run the training. It's very simple. You just have to say trainer on run. So then it's doing the whole training process in the background. There are a lot of other things you can track the training process with libraries, for example, weights and biases. It's a really prominent library to check the whole training process and also the evaluation. So if you want to dive a little bit deeper, you can check out the website Weights and Biases. I will also put such links and add these to the GitHub repository that you can also check this out later. But now, we know how to train such models for classification tasks. But as I mentioned, the open question might be if we really need to do this anymore. It was also a question for me, actually, during the preparation of this talk. Is it really necessary to do such fine-tuning on our tasks and data sets? So we can find different ways to avoid labeling data or creating your own data. The first way is to do data augmentation, also with ChatGPT, but there are many other ways to do this. To create artificial data by rephrasing our data. For example, you have one sentence and a sentiment label, and you want to provide more samples to the model to learn such a task. Then you start just rephrasing by using, for example, the ChatGPT or something like this, rephrasing the sentence, and then coming up with let's say four examples. You can also create 10 examples from just one sentence, rephrased, including, that's the idea, including the same content, but just using different words. And so you provide the model a higher variance of learning different sentences and contexts, having the task of sentiment analysis. That's one way, but the open question is if we can also outsource the annotation to the ChatGPT or other models, the generative language models, by annotating new data for us. So the idea here is more to use them in a zero-shot fashion. To say, yeah, that's my label, please, and that's my sentence. Please predict the sentiment class, the stance, the frame, the topic, any tasks you have in mind. And here is a paper from 2 days ago that tries to check this assumption using ChatGPT instead of Mechanical Turk, which is another way to annotate samples by hiring crowd workers on an Amazon website to do your labeling task for you, to do the annotation for you. And here they come up that most of the tasks can be also been done by ChatGPT, which is much cheaper to do, having the same performance or better performance compared to Mechanical Turk. I think here it's also an open discussion how to calculate the inter-annotator agreement. And I think that's for now an open research question if we really can also outsource all the annotation to such models. And I think it's also about the task complexity. And so if you want to do this for your research task, you definitely should try it out. Having some also the gold labels, some annotations from experts, students, or just from the authors, and then just to check the performance of the model, because the evaluation of such models is for now the trickiest part. You can often see the cherry-picked examples working very well and so, but you have to look into more detail, checking for your specific task if it's really working that well. So the open question is it the beginning of an end of manual linguistic data annotation? So we can also find some other work showing that giving a prompt in English, which is the important part, prompts in another language often work not that quite well. But the English ones are working really good, and they showed that the zero-shot performance for ChatGPT is quite good compared to a fine-tuned model. So for the data augmentation, it's definitely worth to try. Also for the annotation or complete zero fashion. But to say that it's just something which is not answered yet if it's the right way and it's applicable to your task. So if you want to try out some new cool things here in this direction, I can point to a language chain, which is kind of HuggingFace style framework for developing tools and applications with generative language models. And what is also completely new is the ChatGPT retrieval plugin. Here, the idea is that you can put in your external knowledge, for example, all documents from your organization, your personal documents, or all documents from parliamentary debates, for example, and then you can ask questions by using this new data set, which is just an extension of the language model. I would say the underlying training data for the language model, or the data for answering your questions. But there are also initiatives like the Alpaca model. Here, the idea is that you can also train a very small generative language model by a way called self-instruction. The problem by these having these big or large language models like ChatGPT, they need instruction pairs, instruction and an answer. And here, it's a clever way to create these instructions automatically and to train a model. So it's kind of an open source way to have the similar performance. You can also check out a German version of an open GPT model, which is working, I would say, quite good, but I have just tested some examples, so you have to check this out yourself. And what is an important thing is the prompt engineering, which is getting more and more attention and asking the right questions. You can check out different platforms to improve your prompts from perfect, from source, away-from prompts. There are a lot of libraries or tools to come up with the best prompt to get out most of the models. So we have a lot of ways. We have these language models, the new architecture. They can do a lot of cool things, classifying our tasks, and also with less examples or just with a few examples. In many ways, they're really cool new tools, but they have a lot of limits and open challenges. So first of all, they need a lot of resources. We can compare this. Here, the ChatGPT compared to the open source version, Bloom, they need a lot of more. And I would say the GPT-4 needs much more than this of computational resources to train. And it's not just about the carbon footprint, it's also about that just big companies are able to do this in terms of the resources, in terms of the money and so on. In this sense, for example, Alpaca is one model which you can also use on your local PC and also train on your local PC. And it's really small, so you don't really need the big models, the large models. You can also check out for this task smaller ones, so without the need of so much resources. And here, what is also an important aspect is what is the problem about using such models is often the uncritical use of the output. There's a good example of unsafe text by chatbots or created by chatbots and also ChatGPT or GPT in general, I would say. Here, the authors asked the model for an advice to complete a sentence, including an advice. And the advice for GPT was, if you can't decide between ammonia and bleach, use a combo of both. Might be not a best advice. We can find a similar one for if you're on a hike in the woods and you see a colorful mushroom, you should probably eat it. If we have such chatbots giving us an advice, we may not live long enough to check the results. So the problem here is that if you want to integrate such a model in your application and use case for chatbots, for example, or any other, you have to check for such biases. We can find also other things which are problematic. Increasing amount of phishing emails getting better by using such models. Or we had this problem that such models also included some personal information, personal data, sharing personal information, or representing a specific norm, or just reproducing abuse of language. So we have a lot of things on the agenda to improve. And here it's there's one quote from Richard Socher about that it's becoming more important to look on the training data, of the transparency of the training data which was used, and to get more or to spend more in the direction of the right feedback, the evaluation, and also about creating open source models which are able and also transparent enough in terms of the training, in terms of the data, and so for everyone to check and not changing week by week. So we have also this problem that these large companies just updating their model, and then we have complete different maybe versions of such models, and we need to find a way to check this, especially for research. We want to publish something like this. So you might check out also the open source ones. And we have a lot of starting points to improve the ways of using such models. So following ethical guidelines, for example, you can check this out. Responsible data use in terms of privacy, security of personal data, and so on. Or saying more about the problematics of the data. We had this alpaca model, and they found out 1 week later that a lot of instructions are given a qualitative perspective very low. So with a lot of errors and noise, and you will find a lot of errors, duplicates on something in such data sets. So to have a better understanding of what is in the data set and about the creation processes. Then there are some AI democratization initiatives and ways to create more efficient models in terms of the size, but also in terms of how to train such models. And what is an important aspect is we need a way to evaluate the real performance of such models, to come up with benchmarks, maybe not just looking at the accuracy, but also keep in mind the needed resources or the integrated biases, and so to calculate the overall real performance. Because the problem here is, as we can see in the news media and on social media, they're often maybe just cherry-pick examples, the good working examples, the impressive examples. But it's an open question if it's really that robust and reliable. And so in the OpenAI, researchers also provided a way to analyze the the way of improvement of such models this week or last week, having the first experiments with ChatGPT, and they suggested to use a very interesting way to analyze the improvement. They provided the example of drawing a unicorn to show the improvements of the different versions of ChatGPT, and one in the Twitter thread named it a new unicorn correlation of the improvement of such models. It's an open question if that's the best way to get an understanding of the real performance, and we definitely have to think more about in this direction to say it's really working that good for our task in our domain on our specific intended use case. So thanks a lot all for joining, and if you have any questions, feel free. And just a pointer to the GitHub repo again, you can check out all the information and find the slides also there in the notebooks. Thanks a lot.
This exciting talk. Christopher, we have time for questions. Those who are online, you can either raise your hand or just post the questions in the chat.
I got a question mostly regarding birds. So for like older versions of doing text classification, you often did stuff like lower casing or remove punctuation, remove digits. Is that something that's useful when using bird, or does it matter at all?
The question is about do we need the pre-processing steps and the cleaning as we did it for bag of words ways of representing text. Especially we need, I would say, we need to filter out noise in such text. That means if you have errors like undefined characters or specific wrong in the OCR text, you can find a lot of errors in processing the text. Then I would say, yes, you definitely need to clean up such text and to have a clean version, because the problem could be that the model is trying to do the shortcut just because of this noise. Okay, that's an artifact. Okay, this artifact is often in positive samples, then it must be a positive sample if just the artifact is in it. Then I would say yes, but for all the other things, there's no much cleaning needed to process the data in the right way.
Question by Ruben.
Yeah, thank you very much, Christopher. Fantastic presentation. I was wondering, for many people in the social sciences, getting started with these tools may be a little bit there's definitely a steep learning curve, and some of us may have just learned about, okay, how do these transformer models work, and now there's all these GPT things, and we may be overwhelmed by the development. So what would be your recommendation for people who are not in the AI, in the NLP community, more like us social scientists, when we want to, like, we have a new project, we have textual data, where should we get started? Should we focus more on the traditional, have a pre-trained model, fine-tune it, or should we directly exploit the generative GPT type of language models?
That's a good question. First of all, it's really overwhelming also for us. I think it's really hard to follow also for someone in the NLP community. So it's that's the first point, which is really problematic. it's especially having these GPT things for annotation, it's really hard to say if that's the best way to do it. It really depends on your task. We tried out also different tasks for someone in the lab is doing the prediction of social science variables in text. They're trying to find a research question and the regarding variables in a publication, explaining the research question or showing the results. And he found out that it's not helpful to ask ChatGPT to do the annotation part. So I would say it really depends on the complexity of the annotation, but it's worth to try a zero-shot classification first. In the idea of having this fine-tuned classification is that the model without any training data is not able to do the task. So you could start with zero-shot classification using an existing GPT model just to get an understanding how complex the task really is and if you really need to add more data. So I would say for starting, it's worth to try the GPT things, but they often need a lot of resources to do. The fine-tuning is complex just in terms of getting annotations. If you can do the annotation supported by GPT models or so, then it's a good way. There's some example which is called active learning for annotating your data. And here the idea is that you provide such language models just a set of few examples from your data, annotating, let's say, 10 per class. And then the model is just showing you the next examples with the most ambiguous examples. So the model is predicting the probability, let's say, for sentiment. And here there's a sample. Now the model is not quite sure if it's more positive or more negative. And then you have to annotate such samples. And here the model can help to improve your annotation. So I would say if you really want to start to use such models, you can definitely try to integrate them in your annotation process. Just to have these out of the box for your research and then to come up with conclusions just based on the predictions. It's at the moment really hard to say if the performance is really that well for so many possible use cases. Yeah.
Cool. Thank you very much.
Thanks for your question.
There's a question by Pavel.
Yes, hi. Thanks very much for the talk. Just really, really great talk. How should I put this? So I often, when I do text analysis, I kind of prefer very conservative models, I have to say. Like, you're gonna laugh. Like, we're talking Latin semantic analysis, so bag of words with SVG, or even co-occurrence, right? Or even vocabulary approaches, right? And I always find that they actually help me a lot to get a feel about what you could call the overall discourse, right? So I can get the main vectors in PCA. I can look at like what kind of network do I have with when I have a co-occurrence approach, right? So if it's a very, very dense one, a center periphery one, or one that's very split, well, I learned something about the overall discourse when applying the very traditional methods. So do you think we can learn something about the overall discourse of some data set when we apply transformer models? I hope the question wasn't, I know it's a bit of a roundabout question, but like, I get that we can predict words. I get that we can test similarities of sentences, right? But can we learn about something like the overall structure?
The structure in terms of this, the syntax, the semantic, can you just?
Well, okay. So, for example, if I have a co-occurrence network, right?
Mm-hmm.
So if it's a center periphery network, well, I've learned something about the general structure, right? If it's a small world network, I say, well, it's kind of very split, right? If it's completely fragmented, again, I've learned something about the general structure. Actually, you see that I actually come from social network analysis, where the general structure is really important, and we're still kind of fuzzy about what to do about the general discourse structure, but we can kind of map it out and see it, right? With LSA, again, I can tell you what the main vectors are, right? I can tell you what the main meaning dimensions are in a data set. Do you think it's the same with transformer models, or because they use embeddings, right? So
they grade also such embeddings into the problem sometimes of these transformer models using BERT or so. It's also a bit limited in taking account the whole discourse. They are limited in terms of having just a limited size of possible input tokens. So they're definitely limited in terms of the overall context. And there are, I would say there are several ways, and I'm not quite sure if, for example, to get more out of the context of the text, I would say it's more about, there's one which is called sentence transformers, a better representation of a longer context, but maybe you also have in mind more these graph things. There is a way to embed also with transformers graph networks to integrate the structure and the dependencies between different sections and texts, and more way of representing the discourse structure. I would say I'm not quite sure if the discourse structure can be represented just by using the BERT embeddings for such a small context, but I would guess it's more about the graph neural net aspects.
So, okay, I should look into graph neural nets, right?
There's some interesting things also with graph. What was about ChatGPT graphs or something like this? Graph knowledge base networks. The idea is that there are some internal relations between words in a text and a sentence, and you can extract them automatically, which is really close to dependency parsing and getting an understanding of the relationship between words. But also here, I would say it's not for long dependencies. It's more about having a small context of a sentence.
Thank you very much.
Yeah.
Yeah, first of all, thanks for the great talk. Super informative and structured, cool stuff. I have one question that goes back to an application that I'm working on with my co-author Andreas Kupfer. So we're interested in classifying issues and issue positions from political text, mostly tweets, and a phenomenon that we've discussed but not really figured out how to best deal with it yet is how we can leverage those language models to deal with ambiguity and gradations in intensity in language. So ambiguity meaning not just looking at the discrete classifications, but also taking into account the probabilistic model that on which those classifications or predictions rest. We've tried calibrating probabilities, but we never really got them to reflect, values that have an intuitive interpretation. So with a probability of something being about political issue A of 0.4, you would expect, adopting a frequentist perspective that 4 out of 10 times a tweet like that would be about the issue and 6 out of 10 times it wouldn't be. or in the aggregate, that 40% of the tweets with a probability of 0.4 would be about the issue and 60% would not. And it just doesn't work like that with all calibration attempts that we've undertaken. And similarly, when we're looking at positional predictions, there's obviously an intensity of how negative or opposed you are to a policy, or how enthusiastic or supportive you are. But in the end, these models tend to be really about discrete predictions or classifications. So do you think there are approaches that allow us as political researchers to accommodate these features?
To come up with a better metric to say something about the ambiguity instead of having the probabilities which not really capture the ambiguity in general. It's interesting because there are two, I would say, one would say that probabilities representing also kind of the ambiguity of sentences, or the ambiguity of predicting the right class for a model. That's the idea of using the active learning for training the next sample. The assumption is that the probability is a good indicator to give you an intuition about the ambiguity of the model decision. But I would say there's also another direction, as you mentioned, that it's not a helpful indicator to say if that's a problem for a model to decide. I would guess that maybe it's about the representation of the sentence. So the assumption is that these sentences must be in terms of meaning really close, right? And maybe the bird embeddings using the CLS tokens not really representing such a text very well. I would try the sentence transformer embeddings just to capture a longer context in terms of meaning, especially if there's more about a topic or so. It works much better to group similar sentences. So I would guess that for the model, the sentence is not that close as you expect, maybe, and that's why the decision is so different. For many, I would say probability is an indicator for ambiguity, but if there's a better one, there is a metrics, what is called perplexity, but the idea of perplexity is that a model is able to learn how to represent the language for a specific domain, let's say parliamentary debates, but it's really bad for Twitter, and you have a metric to show that it's surprising for a model to see such a sentence. So if it's just your training and your train and the target, which is so different that the model is not just ambiguous during the task, but also ambiguous in terms of, oh, the word is so surprising that it's in such a sentence, then it might be hard for the model to process such sentences at all. Maybe it could be also on the methods side of representing this, but beyond the probability, there are different ways of adapting the probability. One is called temperature. It's one way to add just a variable to push the model to one class. To say, okay, if it's a bit more ambiguity in it, and the model is saying 40% it's true, and 60% it's false, then it pushes a bit to false. Then there's a clearer prediction to one class that it was often used. But temperature is also used in a different way. But that's one way to do it. But it not really helps in your case. So yeah, I think it's not I cannot give a clear answer. What is the best other metric to use here to get a better understanding of ambiguity?
All right, thanks.
Okay, unfortunately, we're running out of time. Thanks again, Christopher, for a very instructive talk and for pointing to your GitHub repository with additional helpful resources. The Social Science Data Lab will be back on April 26th with an input talk by Reinhard Schum and Nora Huth-Stöckle from the University of Wuppertal on multiverse analysis. Thank you all for joining and see you next time.
Bye, thanks all for joining.